So let's look into the details of the E step, or expectation step, as people usually call it. Recall that on the previous video, we derived a variational lower bound, which is a lower bound for the log likelihood which we want to maximize at any given point theta, and it also depends on the variational parameter q, which itself is a distribution. And on the E step, we want to maximize this lower bound with respect to q, while fixing theta to be some value, some particular value. So we can illustrate this situation like this. We have our blue curve, the log likelihood, and we have a family of lower bounds depending on different q. And we want to choose the one that has the highest value at the particular current point theta k, which basically means that we want to minimize the gap between the lower bound and the blue curve. So let's look in details let's derive an expression for this gap by using a blackboard. So let's look closer into this gap between the marginal log likelihood and the lower bound. First of all, we can decompose the marginal log likelihood into a sum of with respect to individual objects, as we usually do. So we assume that the data set consists of individual of the objects that are independent given the parameters. We have this thing, and then we can recall the definition of the lower bound, which we have just derived in the previous video. So this marginal lower bound is sum with respect to objects, then sum with respect to the values of the latent variable, for example from 1 to 3 in the case of free Gaussians. Then the variational distribution q of ti equals to the value and times the logarithm of the ratio between the joint distribution p of xi and ti given the parameters, and the variational distribution q. So let's look how can we simplify this expression. Well, first of all, we may notice that sum with respect to the objects appears in both terms of this expression. So we can take this sum outside the terms to look like this. So sum with respect to the objects times a big bracket. Then we may try to also push this logarithm of the marginal log likelihood of individual object inside the summation with respect to c, so to put logarithms close together. And to do that, let's multiply this logarithm by 1, basically by the sum of the probabilities of the variational distribution q. So this expression is just 1, because it's a valid probability distribution. So this thing always equals to 1. And now, since logarithm of the marginal log likelihood doesn't depend on c, we can put this this thing inside the summation. So we can put it here, and this will not change anything. And finally, we can rewrite the second part, the second term, be sum with respect to the values times again q and times the logarithm of the ratio. And then we can put this summation with respect to the values of the latent variable outside of all the expressions. So we'll have sum with respect to the objects in the data set, sum with respect to the values of the latent variable from 1 to 3, for example, the weights from the variational distribution, times the difference between the logarithms. So logarithm of the marginal log likelihood minus logarithm of the ratio. Of the joint distribution, xi and ti divided by the variational distribution q. And since the logarithm has the property that difference between the logarithms is logarithm of the ratio, we can rewrite this whole expression like this. So it equals to the sum with respect to objects, sum with respect to the values, again weights from the variational distribution Q, times the logarithm of the ratio, so logarithm of the marginal likelihood, P of xi given parameters theta, divided by this ratio, so divided by the joint distribution P of xi and ti given parameters, and this thing should be divided by q, but we can put this q in numerator because it's like division twice. So now to simplify this thing, we can notice that by the definition of conditional probability, this part equals to probability of ti equals c given the data, given xi and theta, times the prior distribution P of xi given theta. And so these two terms vanish because they appear both in numerator and denominator. And finally, we have an expression like this. We have sum with respect to the objects, sum with respect to the values of a latent variable, the values of the variational distribution Q, times logarithm of Q divided by the posterior distribution on Ti. So probability of Ti given C equals to C, given that the data point xi and the parameters theta. So look closer to this final expression. This thing exactly equals to the Kullback-Leibler divergence between the two distributions. So this is KL divergence between Q of Ti and the posterior distribution P of Ti given C equals to C given xi and theta. So to summarize what we have just derived, the gap between the marginal log likelihood and the lower bound equals to the sum of Kullback-Leibler divergences. So this thing will be sum with respect to the objects in the dataset of KL divergences between Q of Ti and the posterior distribution. And we want to maximize this lower bound with respect to theta. So we want to push this lower bound as high as possible. Maximize it with respect to, not theta, but Q. And maximizing this expression with respect to Q is the same as minimizing the minus this expression, right? So it's the same as minimizing this thing. And note that the marginal log likelihood doesn't depend on Q at all. So we can as well minimize this with this difference. So maximizing the lower bound is the same as minimizing this whole difference. And minimizing this difference is the same as minimizing this sum of KL divergences, because this is what this difference is. So maximizing the lower bound is the same as minimizing the sum of the KL divergences with respect to Q. And recall that KL divergences has two main properties. So first of all, they are always non-negative. And second of all, they equal to zero whenever the distribution coincides. So whenever this and this two distributions are the same. Which means that we, by setting Q to be the posterior distribution, So Q of Ti equals to the posterior. We will optimize this, minimize this sum to 0, so to the global optimal. This sum cannot be ever lower than 0. So whenever we achieve 0, we found the global optimal, which means we maximize the lower bound to the global optimal as well. So to solve the problem on the E step, we just have to set the variational distribution Q to be the posterior distribution on the latent variable Ti given the data and the parameters. So to summarize, the gap between the log likelihood and the lower bound we have equals to the sum of Kullback-Leibler divergences between the distribution Q and the posterior distribution P of Ti of the latent variable given the data we have and the parameters we have. Which basically means that if we want to maximize this lower bound, it's the same as minimizing minus lower bound. And since the log likelihood doesn't depend on Q, it's the same as minimizing this difference, the left-hand side of the expression. And finally, it's the same as minimizing this sum of Kullback-Leibler divergences. And as we know, Kullback-Leibler divergences are non-negative, and they equal to 0 whenever the distributions coincide, whenever they are the same. Which means that we can minimize this thing to the optimal value by just setting Q to be the posterior distribution on Ti given the data. So this is our optimal solution to the E step. So just set Q to be the posterior with the current values of the parameters, and it minimizes the gap to be 0 because scale distance now is 0, and so the lower bound becomes accurate at the current point. The gap is 0, so the value of the lower bound equals to the value of the log likelihood.